Good evening, everyone. So, we are going to continue the yesterday lecture on GNSS satellite navigation. So, we were talking about online this outline of principal range. So, the range is equal to time taken into speed of light. So, you can see this is one. For instance, the someone is human is standing here and he's tracking this satellite data, satellite navigation data here. So this is called this is one way travel time is taking place here. So like our mobile mainly based on it mainly provides the position using the L1C, our L2C, depending on the how mobile chip has been designed to provide the location. And this is when you are going to set up the campaign and you are going to track for you are going for mapping our surveying, then you can track satellite like this. So here all the satellites will be tracked depending on the license or how much license you have been provided in your receiver to track the different satellite signal. So when we talk about this positioning, so if we are receiving signal from one satellite only, you see, so it will estimate the distance. So that distance and that location, ultimately you want a location. So the location from one satellite will be anywhere on the sphere, somewhere on the sphere. Okay, so it is very much uncertain where we are on this earth. So when we are using two satellite like this, two satellites, so it will draw a curvature. So once you get the range, so it will cut, so it will cut like this, so it will draw a circle. So we can be anywhere inside the circle, but still it is uncertain where we are actually, because the area is big. So that's why we need at least three satellites to get some approximate idea of our location on the earth, where we are on the earth. So once we get three these satellites range, then here is the position, so it will intersect each other. And you see when the third is intersecting here, so either we can hear our we can hear. So these two locations is giving the possibility of our approximate location. So this can be minimized. Once you have a more number of satellites, you can minimize and you can bring it to meter or millimeter scale, depending on the how you are dealing with the ambiguities. So satellite are like orbiting control stations. Range, distance are measured to each satellite using time dependent codes. Typically, GNSS receiver use inexpensive clocks, like means our mobile, what surveying type of instrument is coming. So these all are using basically quartz clock. So these are not and you know it's basically this clock phenomena is based on oscillation, precise oscillation. So if particle is not very good, like unlike your rubidium and cesium, they are very precise. They are also called atomic clock. So this oscillation is very precise, and in nanoseconds it is not creating any ambiguity. So but in it is that is very costly. So that's why normally we are dependent on quartz clock, and these are they are much less accurate than the clocks on board the satellite. So that's why this is one of the ambiguity. occur in our navigation data. This is the one of the ambiguity, so we have to reduce it. So there is a method to reduce it, that is called single difference sensing and double difference sensing. We will discuss on that in next lecture. So the radio waves travel at the speed of light, so distance is equal to velocity into time. So you see, if there is a clock error like 1 by 10, then the error would be 30,000 kilometer error would be. So it's very very big. And if it is 1 to the power 1 upon 10 to the power 6, you see, so then it will come to down, and but it is not less, it is having approximately 300 meter error. So that's why this nano second then beyond we need to adopt, and so that we can bring it to millimeter to centimeter or millimeter level. So the timing accuracy of position is only as good as your clock. It's very true, and this is a fundamental. To know where you are, you must know when you receive. Receiver clock must match satellite clock to compute delta t. So I hope you are understanding this statement. I already explained about this. So satellite vehicle carry atomic oscillator. I told you, 2 rubidium, 2 cesium each. Not practical for a handheld receiver. So accumulated drift of receiver clock is also called clock bias. The erroneous measured range is called pseudo range. To eliminate the bias, a 4 satellite vehicle is tracked. So here you have 4 equation and 4 unknown. So with the help of that, you can get x, y, z, and b. So if you have a Doppler component, then you can estimate the velocity as well. What is the velocity? Each Galileo satellite has 2 master passive hydrogen master atomic clocks and 2 secondary rubidium atomic clocks, which are independent of each other. So here is a quiz. So let me go through this. So which is the counterpart system of Lorentz? I hope everybody know about this. So it is there are 4 options. So I think you all now aware of this. It's Chakya. Now the second question is Galileo is from. So you know Bedu, GPS, GLONASS, IRSS, QZSS. So Galileo is from European Union. It is not from Russia, Japan, or USA. Then GPS is based on which type of ranging? One way, two way, three way, or none. So all the GNSS constellation is based on one way ranging. That's all. Then GLONASS use following signal. So GLONASS is very different than other satellite navigation constellation. So other uses CDMA, but here GLONASS uses both FDMA and CDMA both. So you know what is CDMA? Frequency division multiple access, code division multiple access. So you must have seen in your mobile this type of signals have been using. Then which is the counterpart or system of alpha? So you know this Chakya, GPS, GLONASS cannot be the answer. It's omega. It's a counterpart of alpha. Then Bedu is from. So you know Bedu is from China. Accumulated drift of a receiver clock is called no pseudo range. Pseudo range is for your distance. Triangulation you're based on the angle measurement. Trilateration is based on the distance measurement. So that's why here is clock bias. clock bias, we use this term to represent the accumulated drift of receiver clock. Okay, then positioning requires minimum number of satellites, so we need at least 3 satellites, but better positioning would be there if we have a more than 3 number of satellites. Then this is the equations for position to estimate the position. So this x, y and z is your user position, okay, which is unknown, it is not known, but x1, x2, x3, x4, like y, like z plus b, these are x, y, z, these are known, and b is also unknown. This is constant factor, so that's why you have 4 unknown, and you need at least 4 equation to get the this 4 this unknown estimated. So p is measured pseudo range, biased range to the ith satellite vehicle. So position of the ith satellite vehicle, they are in Cartesian coordinate. So you must be thinking that what is x, y, z, xi, yi, zi, it's the satellite position. So we need satellite position, real time satellite position, so that we can estimate and this x, y, z and b. And b is the user clock bias in distance unit, can be solved for. So you know this is a non-linear equation, and you have to have so many equations, least square estimations, partial derivative, then this different double differences, so many things you have to do. These equations and all I will discuss in my next lecture. Then to solve the user position equation, one must know where the satellite vehicle. So the navigation and time code provides this. So 50 Hz signals modulated on L1 and L2 signals provides this informations where the satellite position is. So this ephemeris what we are getting through this L1 with the help of your fundamental frequency, it is helping to provide you the real time position of satellite. And you know this Keplerian element, so there are 5 Keplerian elements, so you have to estimate all those Keplerian elements with the help of ephemeris, so that you can provide the different error budget which is related to your rotation of the earth, then flattening, then your shape of the earth, then datum, all this ephemeris is helping in providing all these estimates, and mean mass anomaly, all these are getting estimated with the help of that. So GPS time, so I always when I was not knowing, I was not joined here, I always fond of this, that how GPS time came into the picture, what is the reference for that. So it was always in my mind. So then now I came to know that this GPS time is a reference to 6 January 1980 0000, and 6 January is the first Sunday in 1980. So this is the reference of GPS time. So GPS satellite clocks are essentially synced to International Atomic Clock TAI, and therefore to UTC Zulu time since 1st January 1972 for global civil time. Okay, so this is the GPS time, TAI plus 13 power to S. So since 13 is the leap second, existed on 1/6/1980, so that's why you have to use this leap second to estimate the GPS time, precise GPS time. So GPS time drifts ahead of UTC, which is a coordinated universal time, as the latter is held leap second to accommodate Earth slowing. So delta between GPS satellite time and UTC is included in navigation and timing message. So this satellite vehicle clocks good to about 1 parts in 10 to the power 13. It effectively GPS time starts with 0 at the beginning of each week. So this is the infrastructure of GPS signal. So you can see here, this is the fundamental frequency, means we can say a driver also, where it is carrying this L1 19 centimeter wavelength, L2 23 centimeter wavelength, and this C1 C by A course versus accuracy, P and Y on both L1 and L2, all this, and plus L5 is also. So this L1, L2 and L5, they are basically having fundamental frequency is 10 to the power, sorry, 10.23 megahertz. So you can see here, this is L1, L2, then C by A fundamental frequency is 1 by 023 megahertz. So this is P by Y precise code. These both are having this same fundamental frequency. So GLONASS fundamental frequency is 5 megahertz. So L2, L3 and L4 is basically used for atomic flash detection, means nuclear detection system, NDS. This L2, L3 and L4. So that's why you must you are not very much familiar with L3 and L4, but too much familiar with L1, L2 and L5. Then L5 is mission objective was to for this indoor apps, anti-jamming and safety of life. So this was the objective. And L2C is 1227.60 megahertz, is for pre-operational testing and available on 24 satellites since May 2017. And L1C 1575.42 megahertz, it's coming with the new generation of GPS satellites. So here is the L5 1176, and it's also having same fundamental frequency. L1C, L2C having same fundamental frequency, that's why they are faster and they are producing less ambiguity. So the modernized GPS, it's providing new signals. The second civil signals L2C, then third civil signal L5, then fourth civil signal L1C. So these all came into the picture in the modern GPS. Then comes to precise code. So this P rate is the fundamental frequency, and you see this P code is fundamental frequency is this multiplied by 115, so ultimately it is 1176 gigahertz, and which is your carrier L5. So this generally encrypted into Y code, and anti-spooking requires a special chip to decode. So this has been modulated both L1 and L2, also modulated by navigation and time data message. So this chipping rate is I told you 10 to the power 10.23 megahertz, that is approximately 29.30 m, means 10 times faster than course versus accuracy code, ensuring improvement in time measurement. Therefore the accuracy is approximately 10 times higher than the course versus accuracy code. Then now comes to the course versus accuracy. So this is also known as clear access code. So this is having 1023 or 511 bit gold code, and this GPS GLONASS and L1C is 1020 10230 bit wheel code, originally intended as simply an acquisition code for P code receiver, and modulates the L1 wave only, frequency only. So this is this is the L course versus accuracy code, you can see here. So now comes to the navigation message. So in order to solve this user position, I told you we need the precise information about the orbit, about the satellite position, about the ionosphere, troposphere, then satellite clock informations, then other this capillary element information. So all this is providing by this navigation message, and it is continuously transmitting through your satellite navigation this data. So this navigation and time provides this 50 Hz signal modulated on L1 and L2. Satellite vehicle O1 position information is transmitted in 1500 beat data frame. Pseudo Kaplan orbital element is estimated after that and determined by the control center via ground tracking. So this receiver implements orbit to position algorithm also. If there is some mishappening, means orbit is not good and it is not optimum. So based after receiving all this data, this re-estimating this orbit and all, and it is again this message is transferring to the satellite so that they will orbit in proper manner around the earth. So as I told you, this ionospheric and tropospheric corrections is also done with the help of navigation message. So this navigation message is like this. This is the structure of navigation message. So this db1, db2, db3, so these all are there, and this clock bias coefficient, broadcast ephemeris, then almanac data. So all these are embedded in the navigation message. So this is the almanac. So basically this almanac provides you information about this orbit information, satellite position information, and other important information it is providing through the almanac. Then the range determination from this code observation. So we in the beginning we had discussed that this receiver code from satellite should get matched with the replica signal generated from the receiver, ground receiver. So you see there is a time delay. So this dt, we have to estimate the dt. So how we can do that? So we need this receiver mass and this navigation message. Then we need some all the error budget. So if we can get in good amount, and if we are getting more observation, means at least 8 hours we are getting, so then we can have this centimeter to millimeter level accuracy. And if we have a 24-hour observation, our 2 days 5 days observation in 15-second sampling interval signal and all, so we can have very precise information. Then we can resolve all the ambiguities and we can estimate precise dt. So once we have precise dt, we can have this precise true range. We can estimate this this pseudo range can be the true range, means velocity into dt. So this PRN is, I told you, this representing for each individual satellite. Pseudo range number uniquely identifies each satellites, and PRN provides timing coordination for GPS. Then PRN enable amplification for offset signals. Each satellite sends a unique signal which repeats itself approx 1 millisecond. So this receiver compares self-generated signal with the receiver signals. I told you correlation process, and this synchronization our receiver clock with the satellite clock, and then dt is estimated after the modeling. So this is how you see this replica signal is generating, and this correlation is going between satellite signal and receiver generated signal. Then now comes to this phase observation, our carrier phase observation. So here also same, the only thing this wave has changed. There the wave was a square wave, here the wave is a sinusoidal wave and very precise. So it is having each second having very crucial information. So this wavelength is because in earlier case there was no wavelength, but here we have wavelength, amplitude, everything we have here. So this is 19 centimeter for L1, 24 centimeter for L2. So this receiver compares self-generated phase with the receiver received phase. Number of wavelength is not known at the time of the receiver switch on. So this is one of the this important this error, this that is called carrier phase ambiguity. And as long as you track the satellite, this the change in distance can be observed. The carrier phase ambiguity remains constant. So this ambiguity is always there, and lambda. So this is very difficult to remove, but some after some knowledge and all, we can model this also. Now comes to the satellite geometry. So this satellite geometry can affect the quality of signals and accuracy of receiver trilateration. So I told you last day that this satellite geometry we define with the help of DOP. So that is called positional dilation of precision. So this it is PDOP. Then reflect each satellite position relative to the other satellites being accessed by the ground antenna, our receiver, tracked by the receiver. So this PDOP can be used as an indicator of the quality of receiver's triangulated position, and it is usually up to the GPS receiver to pick satellite which provides the best position trilateration. So when there was no other navigation satellite constellation, only GPS was there. So this was a big problem to get very good PDOP. But now we have a GNSS. So there are so many GNSS satellites orbiting around our this user's positions, user antenna. So that's why we have very good quality, and we are able to get less than 3 as well, this DOP. So this 1 to 3 means very good, and 4 to 5 is good, 6 is fair, and this more than 6 is poor. You cannot rely on the geometry of the satellites to determine the position of your location. So that's why, and you must have this between 1 to 3. So satellite geometry can affect the quality of signal and accuracy of receiver trilateration. So this distribution of satellite is very important in space with respect to your user antenna, means your ground antenna, how much satellite it is tracking. So this they must track, the satellite must be distributed in a good manner, so that this GDOP, geometrical dilution of precision, should be very good, so that it can estimate the latitude, longitude, height and time. And PDOP is estimating the latitude, longitude and height only. And HDOP is good when this latitude, when we are only thinking for latitude and longitude. And vertical DOP is good when we are only including the height. So if the distribution is like this is good. So we should have like this. And if you have distribution of satellite is like this with respect to your ground antenna, and it is transmitting the signal continuously, so it is comes under poor DOP. So you cannot use it, because when you will have true range, so when it is going to draw this your curvature, so it will not draw in a very accurate manner. So that's why it is called poor. Now this satellite geometries, so you can see the ideal satellite geometry is, so this is ideal geometry, and you see the curvature. So it is coming like this, your positioning is coming like this. So good satellite geometry. But when satellite is skewed, satellite geometry is there, so you see, so when you have this range, so curvature is going like this, and you see it is sparse, so you have very big uncertainty, so you can be anywhere around this. So that's why it is very difficult to determine your precise position when the geometry is like this. So ground control, so this is very good when we are going for this georeferencing and improving our geo coordinate of our satellite data. This ground control for photogrammetry. So the objective is of the ground control is to locate the ground position of the points which can be identified on the aerial photographs, our images. So it can be age of the some these roads, our some this reference point locations where you can where you are standing on the ground physically. That location can be relocate on your satellite data as well. So we should pick all those location to get the ground control point with the help of DGPS, and then we can improve the your geo coordinate and georeferencing after this using this georeferencing software. You can do in ArcGIS, ERDAS, and where you can do that. And it is very much it is necessary in order to establish a position and orientation of each photograph in space related to the ground. So this is the ultimate goal actually of the this satellite data, to represent the satellite data and it should be the physically represent all the informations of this whatever available on the earth. So enable the photographs to be used in compilation of planimetric these maps, topographic maps, and mosaics. So the first step of this ground control is the basic survey, and then the photo control. Then second step is to where how many points you have collected, all you can apply on the data, and you can control the this orientation and position. The accuracy of finished photogrammetric product can be no better than the ground control, but upon which they are based. So GCP, how you can collect the GCP should be sharp, as I told you, positively defined and identifiable on the ground as well as on the satellite image. Then favorable location. Then minimum 3 GCP for space resection and more for least square adjustment. And for orientation of stereo model, minimum 2 horizontal and 3 vertical, and practically 3 horizontal and 4 vertical. So this is how you can do that. Then these are DAM which you can download, and this is open source DAM. So this LOS pulsar, there's then LOS prism, then tandem X 90 meter. So these all are there, and then Cartosat DAM also is coming with 30 meter resolution. Open DAM is 30 meter is coming. So these are very good DAM, and vertical this resolution is maybe less, because for if you want a very good vertical resolution in your DAM, then you must have this very precise GCP. So you have to collect at river, then you have to collect on the this topography, then mountain, roads. Then if once you have a 15 GCP, 20 GCP for suppose 30 kilometer into 30 kilometer swath, Then you can ortho rectify, and this after that georeferencing, you can improve the vertical accuracy, vertical resolution of this dam, because spatial resolution is always good, but this vertical resolution is not always good in open source dam. So that's why if you are doing very sensitive work, so fore and after images are available in from Cartosat satellite, and you can use to make your dam, and with the help of GCP. These are the IGS stations which I was talking about yesterday. So you can see this these are the IGS available in Indian territory. So you can see this Jodhpur, Lucknow, Kanpur, Hyderabad, Bangalore. These are so, and here you can see the all around the earth, and it is mainly controlled by UNESCO and NASA, and they are using this to make the precise datum also, so that this we can know how this mass redistribution is taking place, because so volcanic activity is taking place, then your earthquake is taking place. So all activity are happening not only on the land terrestrial, but it is also happening on in the ocean also. So we should have very precise informations. So sometime when this major mass redistributions takes place, so we need to have new datum, so that we can understand and we can study the geodynamics in very systematic and accurate manner. Then this is the user requirement in positioning accuracies. So you can see this less than 20 centimeter we need when we are going for this geodetic infrastructure, fault monitoring, construction survey, engineering survey, geodynamics. So even in for geodynamics, even we need millimeter accuracy, because our earth is moving with the rate of 50 millimeter per year, and when you are entering into Himalaya, it is again decreasing and it is going to 33 millimeter per year. You know why? Because our Indian plate is also moving, and when you are going to your Badrinath, our Kedarnath, so in that region your velocity is getting modulated. So there is not only Indian plate movement, but there is a Eurasian plate movement also. So both are so one plate is going down, one another plate is going up. So due to that your velocity is basically getting modulated. So that's why when we estimate the velocity with respect to India fix, so we see that approximately it is coming 18 millimeter, 15 millimeter with respect to Indian plate. So that it means that this Badrinath and all, which they are sitting on this higher Himalaya, and they are on hanging wall actually, and they are coming toward us. So we all came to know about this because of this space based geodetic measurement, because it is providing millimeter accuracy. So this land, you can see this earth moving, road, grading, agriculture, mining, urban cadastral survey. All this is required less than 20 centimeter survey. Then marine, here you can do this dredging, then pylons positioning, then airborne, this cat 2 3 sensor positioning. All this is required less than 30 centimeter accuracy. Then comes to your accuracy, your 0.2 to 1.5 meter is required in your resource management mapping, GIS database, utility mapping, highway survey, legal survey. So here you don't need to have a very precise measurement, but if you have a coarse measurement, you can use that and you can get good information about all this information. Then on land, this facility survey, mapping our GIS, highway surveys, rural cadastral survey, precision farming. So all this can be provided in this this accuracy for this land. Then marine docking, bioposition, all this can be get through this accuracy. Then 1 to 5 meter accuracy we need for GIS data collection, site specific farming, navigation, then in on land, automobiles, emergency, public tracking, mapping. So we are 1 to 5 meter is okay. We can work with all this objective for all this objective. Then in marine we can do this channel, then cabling, transport research, then harbor entry. All this can be managed by this accuracy. Then sensor navigation, oceanic is also. Then 10 to 100 meter, very coarse resolution. So this in geomatics reconnaissance we can manage by this accuracy, and navigation area navigation, and then in marine harbor approach oceanic can be managed with this accuracy. So that's why there is a different requirement. You see, there is a different requirement. So it is not that you always need very robust instrument, robust this satellite, this receiver and ground receiver and ground antenna for all this objective. So that's why there are different generation and different types of receiver as well as antenna to measure and to fulfill the requirement of this different objective, so that people can use their budget in optimum way and they can go for their objective. But for this this is the costliest affair, and this is these days so many these ventures and companies are there, like Trimble, Leica, then Indian their Indian companies, the European agencies also manufacturing these days very precise this receiver and antenna. Then Japan is also Topcon. So they are doing that, and they are giving good these accuracies, because here you are not only dependent on this reducing the ambiguities, but you want less this error on while receiving the data as well. So this type of antenna, type of receiver, so it matters a lot. So when you have very robust antenna and very robust this thing, so receiver, then you will have less error through all this measurement. So then you can focus only on the major error which is associated with the measure while this signal propagation, when signal is propagating through the medium. And so then whatever the error is coming into the picture, so you are focusing all those error, reducing the error only. So you are not looking all those error which is occurring due to different means bad quality of antenna and bad receiver. So that's why when you are working in this accuracy, so selection of antenna and receiver matters a lot. So then this, you see this earth, and this is moon. So you see this is the future actually, and this is earth based tracking, an approximate range of a GPS like moon beacon here. So it will go and come like this. So range of omnidirectional signal from moon beacon will be, so it will be like this. So it's a very unique this mission is going to happen in near future. So different GNSS surveying techniques for mapping and monitoring. So here you can using GNSS for surveying. So you can go for static measurement, rapid static, kinematics, real time, and then accuracy and observational time, then this recommended recording interval. So these are the different surveying techniques. So static means you have kept your this antenna at one location, and you are only measuring at the center of that tripod continuously. Means depending on your objective and accuracy demand, what objective, for what objective you have gone for the measurement, and that's why you have gone for this static measurement. So like when we are planning for this landslide monitoring, land subsidence monitoring, then dam monitoring, then active tectonics, then fault monitoring, crustal deformations. So these all requires static setup of GNSS antenna and receiver. So and it should be very very robust. So it comes into static measurement. Then also this GCP is also part of that. So some GCP is static and some GCP is rapid static kinematics also. So kinematics means when you are going to map the area, you want to going to map the length. Okay, then you need to have this kinematic measurement. So and these days this technology is very improved. So real time broadcast error ephemeris data is coming into the receiver, and real time centimeter accuracy is we people researchers are getting through for this kinematic measurement. Then this real time is always there. Then and then accuracy and observational time, that yes. So as I told you, what is your accuracy requirement and precision requirement. So based on that you will define the observation time. So if you are defining at minimum 8 hours, so you can resolve most of the ambiguities to get the precise look this latitude, longitude and time and height as well. So but if you have 1 day, 2 day, 3 day, 5 days data, so then you can have very fixed millimeter accuracy solution for your this position static information. Then recommended recording interval. So see when we are working for this earthquake, so if we are keeping 15-second interval, so can we record the earthquake signal? No, we cannot, because when earthquake occur, so it is the transient signal, so it occurring very short interval. For a short interval it is occurring, so mainly 20-second, 15-second, sometime 30-second, depending on the energy and how much it is attenuating. So that's why it is necessary to keep the very high sampling interval, means 1 second. So if 1 second sampling interval is there, so then you can record the earthquake signal when it is going to occur. So but it is not always a good phenomena, because it takes more storage and all. So that's why depending on your storage and all, you define this 1 second sampling interval to acquire the GNSS signal in your receiver. And normally we fix for static measurement we fix the 15-second, 30-second, like that, because this is the minimum requirement, 15-second, 30 seconds. So with the help of that you can means get a very good volume of data, and you can resolve all these ambiguities. And when you are going for this GCP, ground control point, so see half an hour data, 1 hour data is sufficient, because your satellite is having accuracy of like 5 meter, our 8 meter, means if I talk about list 4, it is 5.8 meter resolutions. If I'm talking about cartosat, it is 2.5 meter resolution. And there is, means I'm talking about dam cartosat 1. So there is a different generation of cartosat series also. So there is better resolution is 0.6, 0.7 meter. So it is very high resolution. So that's why when you are going to use all those cartosat series data, so you need to have at least 2 hours data to get the very precise centimeter accuracy, so that you can use to orient and to define the positions accurately on the satellite image. Then what GPS can tell us about Earth? So you see the snow depth. Nowadays people are working on using or snow depth using GNSS signal. Then this GPS, this snow depth measurement in hard to reach areas, because it is very hard to reach in these areas. So once you have set up this type of instrument over there, so you can very easily detect the this snow depth, how the depth is fluctuating over the time. You can do that. Then ice height. So changing ice heights indicates how much fresh water is stored by our being lost from the glacier. So this can be done with the help of GNSS. Then sea level. As the tile goes, GPS can measure local, regional, and global changes in the sea level. So this is very good to track and monitor the sea level as well. Then vegetation. So this these days reflectometer is coming, GNSS reflectometer, and people are using those to monitor the crop health and crop size, how it is growing and how it is going down. So all vegetations can help the plant growth. So it not only defining the plant information, but you can you can do the modeling, and you can know what is the health of the soil as well. Excuse me. The soil moisture. So soil moisture measured over buried and region indicates how much precipitation evaporated back into the atmosphere. So this also possible with the help of GNSS. So this comes under your reflected signals, gives us information about the earth water cycle. So very good information. Then GPS signals sends information about the atmosphere. So people are not only dependent, not only working on land, but people are working on this atmosphere also. So upper atmosphere, lower atmosphere, ionosphere, troposphere. So everywhere now GNSS has an immense application actually. So this how ionosphere, this, that's why this L1, L2, L5 signal is there to estimate the and to study the ionospheric behavior changes temporally. Spatial temporally change can be done with the help of GNSS. So and troposphere also. So you see this refractive index. So refractive index mainly this water vapor, pressure, temperature, all these are changing drastically, and due to that this cloud burst, this sudden this cloud condensation, all this, and your various climate changes taking place, and all this can be done with the help of GNSS. Then here GPS provides position, gives us information about Earth many system. So as I told you, this tectonics, water resources, glaciers, earthquakes, and volcanoes. So you can do the volcanoes monitoring, earthquake monitoring, glaciers monitoring, water resources, how water. So nowadays these researchers are modeling this GNSS data to model the aquifer, that how this water table is fluctuating, and it is going up and down in the aquifer in the Vedas zone. So this is very much possible these days with the help of GNSS. And tectonics, as I already discussed about this. Then these are the different applications, other applications of NSS and Navic also. because this is made in India. So this terrestrial, aerial, marine navigations, disaster management, natural resource management, then tracking, fleet management, integration with mobile phone, precise timing, mapping, surveying, and geodetic detail capture, terrestrial navigation aid for hikers and travelers, visual voice navigations for drivers, atmospheric studies, crystal movement, deformations, business solutions. So still we are working on that, but most of the applications is very much possible with the present status of the INSS signal and all. So these are some more application of GNSS. So you can see the beautiful image of this GNSS campaign setup in mountain ranger, and these are the some references which you can go through that, and you can get more information about this literature and this other GNSS satellite constellation, and this data as well. You can get the some open access data from this UNAVCO, CTTIS, for course, SOPAC, all this you can get. Thank you very much.